Welcome to this video. And in my previous video, I introduced the concept of describing functions as relates to nonlinear systems. And we noted that the describing function is a frequency domain method of analyzing or predicting the behavior of nonlinear systems. We're able to look at how you'd establish the describing function for a two-position relay. And in this video, then I would pick up saturation as our nonlinearity, and we proceed to determine its non-describing function. So we take up saturation as our nonlinearity, and we proceed to determine its describing function. Saturation can be described as follows. If this is our input and our output, initially there exists a linear relationship between the input and output up to a certain point of the input, where the output remains constant regardless of the increase in input. And this can be taken to be a line with a gradient k, a line with a gradient k. And if this point is S along the input, and this is negative S, that means the magnitude will be Ks, and at this point, the magnitude will be negative Ks. So this is our nonlinearity. Saturation, the output bears a linear relationship with the input up to a certain point when it remains constant. And as we said, this is a nonlinearity that is exhibited mostly by amplifier systems. Let's proceed to determine the describing function of this nonlinearity. So we draw the nonlinearity as usual. The nonlinearity as follows. So a linear relationship and then remains constant. So this is Ks, and this is negative Ks. This is S, and this is negative S. This is our input and our output. Next, we draw the sinusoid, as we explained earlier, the process of coming up with a describing function. We draw the sinusoid. So if this is our sinusoid, let's make this straight. If this is our sinusoid, okay. For our sinusoid, we need to draw a line of negative 45 degrees from this point. And then we pick up all the points. So I'll first need to move this axis up here. So this can be extended as our new axis. Our axis now of omega t, and our function as a function of omega t, the output. So the nonlinearity will be chopped at this point. The sinusoid will be chopped at this point. And also on this other side, we'll have the nonlinearity chopping the sinusoid. So we need to pick the following points as well. So we need to pick this point. And we can call this angle theta 1. Then we need this angle. This is theta 2. We also need this angle. which is theta 3, and this angle, which is theta 4. So we take those points up. So there is this point. There is this point. This point. And this is this point. Then we also need the pi. So I'll need to pick this point, which is our pi. Then I also need the 2 pi. This point. So we pick up also this point. So we can label them up here as theta 1. This is theta 2. This is pi. This is theta 3, theta 4, and 2 pi. Then we need this magnitude as well. So this magnitude and this magnitude from the negative half cycle. So from 0 to theta 1, we notice that both signals are increasing and therefore a linear relationship exists. But from theta 1 to theta 2, the signal remains constant. Then starts decreasing at this point all the way up to theta 3. So there is that sudden fall. Then remains constant up to theta 4, and then starts increasing up to 2 pi. And this becomes the periodic signal, which is a description of our nonlinearity saturation. Next, we need to determine the describing function from the periodic function. Remember, we need to determine n of omega t as a1 cosine omega t plus b1 sine omega t. Since we said we are taking odd symmetry, our a0 is equals to 0. And we notice that our signal, if we are to integrate from 0 to 2 pi, is the same as integrating from 0 to pi and multiplying by 2, because the area from 0 to pi is the same area as from pi to 2 pi. Similarly, if you were to get symmetry, or we were to integrate up to pi over 2, so if this is our point pi over 2, then this region from 0 to pi over 2 is the area below the curve is the same as the area from pi over 2 to pi. That means, again, we can integrate from 0 to pi over 2, but then we'll have to multiply our integral by 4 because it's a quarter of the total area from 0 to 2 pi. We can proceed then to determine our function as follows. Now, from 0 to theta 1, from 0 to theta 1, we notice then our signal is km of t. That is our n of t, which can be written as km, the sine of omega t, from 0 to theta 1. Then from theta 1 to pi over 2, it's a constant at ks. Okay, from theta 1 to pi over 2, this region is a constant, which is ks. And therefore, we will be integrating the signal whose value is Km sine omega t from 0 to theta 1 and Ks from theta 1 to pi over 2. We proceed to determine our values as follows. And again, for odd symmetry, we also noted that for odd symmetry, A1 is equals to 0 when we evaluated the integral for the two-position relay network. And therefore, we'll proceed to determine our constant B1. By definition, B1 is defined as 2 over t, the integral from 0 to t of n of t, the sine of omega n omega t, that's the sine of omega t, d of omega t, sin n is 1, which can be written as initially the integral from 2 to 2 over pi, the integral from 0 to 2 pi of n of t, the sine of omega t, d of omega t. And we said it's the same as getting 4 times the integral from 0 to pi over 2, which you can write as 4 over pi, the integral from 0 to pi over 2, n of t, the sine of omega t, d of omega t. This integral can be written as 4 over pi, the integral from 0 to theta 1 first of the signal. From 0 to theta 1, the signal n of t is Km, the sine of omega t, and then we multiply this by sine omega t, d of omega t, plus the integral 4 over pi, the integral from theta 1 to pi over 2. The signal is Ks multiplied by the sine of omega t, d of omega t, which we can proceed to write as follows. So it will be 4 Km over pi, the integral from 0 to theta 1 of the sine squared of omega t, d of omega t, plus 4 Ks over pi, the integral from theta 1 to pi over 2. So this is theta 1 pi over 2 of the sine omega t, d of omega t. Sine squared function can be written in terms of the cosine function as a double angle as follows. So this is the same as 4 over Km over pi, the integral from 0 to theta 1 of 1 minus cos 2 omega t over 2 d omega t plus 4 Ks over pi, the integral from theta 1 to pi over 2, the sine of omega t, d of omega t, which will be equal to, so this gives us 2 Km over pi, and you multiply out by a half into, we integrate 1 with respect to d omega t to get omega t, and then minus the integral of cosine is sine, so this becomes a half sine 2 omega t, and the limits are from 0 to theta 1 plus 4 Ks over pi. We integrate this to get the negative of cos omega t theta 1 to pi over 2, which will proceed to get us 2 Km over pi into, so when omega t is theta 1, we get theta 1 minus a half sine 2 theta 1, sine 2 theta 1. When omega t is 0, this will be 0. When omega t is 0, the sine part will also be equal to 0, so we get that part, plus 4 Ks over pi into the cosine of pi over 2 is 0, so we'll have minus 0 minus minus, so that means plus the cosine of theta 1. So our function can now be written as 2 km over pi, 2 km over pi into theta 1 minus a half the sine of 2 theta 1 plus 4 ks over pi, the cosine of theta 1, which we can write, we can break this into parts as follows. We can write these as 4 km over pi, or you can write this as 2 km over pi theta 1 minus km over pi, the sine of 2 theta 1 plus 4 ks over pi, the cosine of theta 1. Then we evaluate the following. At theta 1, the signal can be defined as follows. Take you back to the signal. At exactly theta 1, the function can be defined by ks, and then for the signal defined by km sine omega t can also be written as km sine theta 1 is equals to ks. We can write the following. At theta 1, we can write ks is the same as km sine theta 1. And we notice that sine theta 1 will be equal to s over m, and theta 1 will be the sine inverse of s over m. Okay, sine theta 1 will be s over m, and theta 1 will be s inverse sine inverse s over m. At the same time, if you have a right angled triangle, if this is theta 1 and the sine is opposite over hypotenuse, so s over m is the sine of theta 1, we notice that this is going to be m squared minus s squared square root, such that the cosine of theta 1 can be written as m squared minus s squared square root divided by m, which is the same as the square root of 1 minus s over m squared. If you have to put all the terms under the square root, and this is the cosine of theta 1. So we have the cosine of theta 1. We have theta 1 in terms of the sine inverse of s over m, which we can replace into our describing or our function n of t. Our function n of t can now be written as, if we factor out in both cases 4 over pi, we'll have this as km over 2. Theta 1 will be sine inverse s over m minus 2 km over 4. We multiply by, then we have sine 2 theta 1. We can break it down into two parts, into the sine and cosine part as s over m, and then the square root of 1 minus s over m squared, plus, then the other term was ks, and then the cosine of theta 1, it was 4 ks over pi, cosine of theta 1, the cosine of theta 1 is the square root of 1 minus s over m squared square root, like that, which you can write as 4 over pi into km over 2 sine inverse s over m minus, then you notice that this will be a half, will cancel out. This will be a half Ks plus Ks, that will give us a half, plus Ks over 2, the square root of 1 minus S over M squared, which you can proceed to write as, we can factor out Km outside and write these as 2 Km over pi because of these two into the sine inverse of S over M, this term, plus K is outside. Then we'll have this as S over M because we have introduced M here. So K over M, S over M, and then the square root of 1 minus S over M squared. And this is our signal N of T, which is our output. The describing function, as we said, is going to be given by N at an angle of 0 divided by M at an angle of 0, which will be equal to, so it's this function, we divide by M, and the M's will cancel out to get 2K over pi, the sine inverse of S over M plus S over M, the square root of 1 minus S over M squared. And this becomes the describing function for our nonlinearity saturation. This is our describing function, which we said is a function N of M and omega, which is obtained or given in this expression. And that is my end of my presentation, where we've been able to determine the describing function of the saturation nonlinearity. Thank you for watching this video.